sampling design, positioning sampling units in the landscape. How do we decide where to put sampling units when we're determining an appropriate sampling design? Decisions about positioning sampling units are made with respect to the need for good interspersion of sampling units throughout the population or area of interest. And so they are influenced by the type of vegetation, the spatial distribution or patchiness of the vegetation, as well as the size of the area of interest. It's also influenced by practical constraints of time and cost, as well as the need for randomization. There are various approaches to locating sampling units, and we're going to examine the most common approaches here. Simple random sampling is one of the most commonly used approaches for sampling. With this method, each sampling unit has an equal probability of being selected, and the selection of sampling units is independent. So if any one unit is selected, it does not influence or impact the selection of any other units. Simple random sampling is very commonly used, and it's best in smaller, relatively homogeneous areas, and also when the required sample size is not excessively large. The advantages to simple random sampling are that the data are relatively easy to analyze and that it meets most statistical assumptions of independence. Potential disadvantages is that you can have poor dispersion of units throughout the area simply by chance or random selection of the sampling units, and it can potentially be inefficient, especially in larger areas. There are a couple of common approaches to randomly locating sampling units, and the first is the coordinate method. In this case, we usually start off with a map or a schematic diagram of the area of interest, which you can see here in this black outlined area, and then we superimpose an XY coordinate system over the map. We then randomly select pairs of X and Y coordinates so that we can locate a random point within the area. If this random point occurs within the area of interest, we would keep that point and it will become a sampling point. Sometimes the coordinates will occur outside of the area of interest, and so we would reject those points. Now sometimes there's a problem, especially when we're using transects. We can actually have randomly located points that fall within the area of interest. But if we're using transects, they could extend outside of the area of interest. And we don't want to sample outside of the specified population or area of interest. In this case, we could reject these points. The disadvantage of rejecting points, though, is that effectively reduces or shrinks the effective size of the area that we're sampling. And so we would artificially reduce the area outside or near the boundary of the area of interest. One way of dealing with this problem is, instead of rejecting this point, would be to extend the transect to the boundary of the area of interest and then bend it back or angle it back into the area of interest, and that way we wouldn't be throwing out that point. Another approach for simple random sampling is the grid cell method. In this case, the area, or again a schematic diagram of the area, is overlaid with a virtual grid. And the grid cell size and the shape of the cells is equal to the size and shape of the sampling units that we plan to use in the area. We then randomly select different grid cells and we sample without replacement. This allows us to use randomization to independently locate sampling units. Now, it is important to note at some point that doing this on a map is one thing, but then being able to locate where these sampling units actually go on the ground is another. And oftentimes we have to use different approaches, such as pacing, using a compass and physical markers in the field, or using GPS with a good map in order to accurately locate these sampling units on the ground. Because of there's the randomization of selecting units, you can end up with a sample that may under or over represent certain areas with this approach. So if we look at 3 different images that show different random samples located or imposed over the same area, we can see that we have good interspersion of sampling units in the image on the left and in the middle, but that we have kind of a skewed representation where there are far more sampling units on the left side of this area than over here on the right. And that is a potential problem that is inherent with simple random sampling. Another approach to sampling is restricted random sampling. And this is best done when the number of samples that we can take is restricted or it's low. We just can't afford to take the time to collect a lot of data. And so it allows for very good interspersion of units. The way this is done is the area is divided into segments, as you can see here, and then within each of these equally sized segments, a sampling unit is located randomly. We then randomly locate another sampling unit in the next segment and do this for all of the segments in the area. Again, the advantage to this is good interspersion, although occasionally we can run into a problem where we have 2 sampling units that randomly fall very close to each other. If these units actually measure the same plant or the same plant clump or group, then that can become a problem that we need to be aware of. Because usually you don't want to sample the same individual twice. It would be overrepresented. Stratified random sampling is a sampling approach that is very commonly used to measure attributes in natural resources. With stratified random sampling, we stratify an area into subtypes based on classifying characteristics, such as vegetation type, soil type, ecological site, or landform. The important factor is that we never stratify based on the attribute that we're measuring. So if you were measuring cover, you wouldn't stratify your area into strata that have high levels of vegetation cover or low vegetation cover. Here we can see an example diagram of an area that's been stratified into ecological site. So we've got loamy upland here in the buff color, which represents about 50% of the area. The gravelly hills represents approximately 20% of the total area, and the draw ecological site represents about 30% of the total area of interest. With stratified random sampling, we allocate sampling units to the strata, and we have different approaches for those for that kind of allocation. The advantages of stratified random sampling are that it provides a very efficient approach to sampling. We can get improved quality of information when we're working in a variable environment, and the data from each of the different strata can be analyzed separately or they can be lumped together. There are different approaches to allocating the units to the strata, and we're going to examine two. The first is proportional allocation. In this case, the allocation of sampling units to the different strata is proportional to the relative area of each strata. So in this example that we have, if we decided that we could only position 20 sampling units in the entire area, we would then allocate 10 sampling units to the loamy uplands because it represents 50% of the area. Gravelly hills would get 4 sampling units because it's only 20% of the total area, and the draw, being 30%, would get 6 sampling units allocated. Another approach is called optimum allocation, and this aims to achieve the best level of information for a given sampling effort. With optimum allocation, the allocation of sampling units to each of the strata is weighted by the variability of the strata. And so, in order to apply this approach, we have to have some information about the variability of the different strata. So let's take a look at an example using this same area of interest. And we're going to assume that we did some pilot sampling which indicated that the Gravelly Hills ecological site had the highest amount of variability of the 3 ecological sites. And remember that the Gravelly Hills has the lowest proportional area, but it has the highest variability. So with proportional allocation, this is the distribution of sampling units that we would have allocated based on proportional allocation. So with optimum allocation, we want to consider first the proportion of the area, which we already knew was 50% for loamy uplands and 20% for gravelly hills. We now have some information about the variability of the attribute of interest in the ecological site. And we can see that gravelly hills, this variability is represented by standard deviation here, and that gravelly hills is the most variable with the highest standard deviation of 50, while the loamy upland has the lowest variability with 20. And we need to develop a weight a weighting system. And so what we do first is we multiply the proportional area of each of the strata by its respective standard deviation and come up with a weighted value. We then sum these weighted values and come up with a summed weight. The next step is then to take the weighted value for each of the strata or ecological sites and then divide that by the summed weight, and that will give us a new weighted value. That value is then multiplied by the target number of sampling units that we plan to put in the area. So if you remember, we planned on 20 sampling units in this area, and so what we get are, by multiplying 20 by this weighted value, now instead of having 10 units in the loamy upland, we only need 5. And that's because the loamy upland, the attribute has less variability in the loamy upland, and so we need a smaller number of units in order to precisely estimate the value of that variable. With gravelly hills, however, because that area is more variable, we need to increase the number of units in gravelly hills. So instead of having 4 units that we had with proportional allocation, we now would allocate 11 units in the gravelly hills. And that's simply so that we can get a more precise estimate of the variable of interest. So this is a far more efficient approach to using stratified random sampling. Systematic sampling is very commonly done in certain applications for sampling, and this involves the regular placement of sampling units. We divide the area into equal segments and then randomly locate the first unit. We systematically place subsequent units relative to that first one. So this first transect, belt transect, was randomly placed, and then each subsequent one is placed at an equal distance from the next or adjacent transect. Another approach is to use a common combination of transects and quadrats. And in this case, the first transect is randomly located, and the location of the first quadrat on that transect is also randomly located. The location of the other quadrats on that transect are then equally spaced based on the location of the first quadrat. The next transect is located, and in this case, the first quadrat is randomly located on the transect, and each of the other quadrats are spaced at equal distances apart along the transect. And so this is done iteratively throughout the area. This approach is very commonly used to measure frequency, plant frequency. And if the quadrats are spaced far enough apart, they can be considered independent sampling units. In some situations, depending on the spacing of the plants as well as the spacing of the quadrats along the transects, it may be more appropriate to consider the transect as the sampling unit. It all depends on the sampling objectives and the specific situation. The advantages of systematic sampling, as you can see, is that we have very good dispersion of sampling units throughout the sampling area. And this is far more efficient, oftentimes, than random sampling. Potential disadvantages are that you can either under or overestimate the attribute if there is a very regular pattern in the vegetation. And there is the potential for bias because these units are not randomly or independently located. Selective sampling is also called subjective sampling, is when sampling is restricted to key or critical areas. With this approach, we use this when the focus is on providing information that's driven by very specific management issues. So if we know that we want specifically to have information about a key or critical area, then we oftentimes will use this approach. Now, it is a non-random approach, so with non-random selection of the locations, and so there is the potential for bias that must always be considered. But this is very often used for certain applications in natural resource management. Cluster sampling is another approach in which we measure small-scale variation within a cluster of individuals. And it's best done when it's very difficult to take a random sample of the element of interest. So let's see how this is done. In this situation, we randomly locate a transect, and then we measure the attribute of interest on each one of the individuals that falls within that belt transect. Here again, we see another belt transect that's randomly located, and then every individual that occurs within that belt transect is measured for that, the value of that variable, the attribute, is measured. Double sampling is an extremely efficient approach when we need to estimate a variable that is usually very costly or difficult to measure. So there's a difference between estimation and measurement. With double sampling, we incorporate frequent estimation and infrequent measurement. Double sampling is very commonly applied to production estimates or estimates of plant biomass, because biomass is very time consuming to measure, usually done by clipping, and it can be estimated, but it's also very difficult to estimate. So the way this works in this situation, what we do is we have quadrats in which after a certain amount of training, you would estimate the amount of biomass in each one of these quadrats, and then in the fourth quadrat, you both estimate and clip. And so you have both an estimation and a measured value. You then repeat this process through your sampling of estimating frequently, and then infrequently clipping or measuring. And so by the time we're done with this example, we've got 12 quadrats in which we have estimated the biomass, and 3 of them have had measurements taken or clipping done as well. The estimated variable is then correlated with the measured variable, and so we use regression analysis to do this. And if we have a good, strong relationship between the measured value and the estimated value, we can then apply the regression equation and convert these estimated values to come up with a more precise estimate of biomass. So that's how double sampling is done. So to conclude, our choice of sampling design is directly tied to the characteristics of the population and the environment, the practical constraints of time and money, and both our management and sampling objectives. All of these factors are considered when we determine how to position sampling units in the landscape.